In a universe where meeting your anti-self could lead to vanishing in a flash of light, fortunately, we have a different kind of doppelganger, your digital twin. As Professor Stephen Hawking famously said, if you meet your anti-self, don't shake hands. You would both vanish in a great flash of light. But unlike its quantum counterpart, your digital twin is a pristine projection of yourself, tirelessly tackling tasks with precision and efficiency. Would that be for real now? Too good to be true, yeah. It is for real that we encounter our digital twins today, hovering about in a multitude of systems and processes, helping us reach places we cannot go ourselves and preemptively solving issues in the horizon. Stay strapped to your seat while we show how your digital twin goes places. Join us in this fascinating ride as we explore the incredible capabilities of digital twins, from revolutionizing manufacturing and healthcare to unlocking limitless possibilities beyond. Digital twin is a computer-generated replica of a physical object or system. This digital copy accurately models a real-world entity, such as a wind turbine or an entire city, and allows for the simulation and analysis of its physical behavior. The concept of digital twins started with the rise of advanced technology like computers, sensors, and the internet. These tools allowed us to collect a ton of information about real-world objects and create detailed digital versions of them. Although the concept has existed for several decades, with the advancements in technology, particularly in the areas of Internet of Things, artificial intelligence, and cloud computing, today we witness creation of highly detailed and precise digital representations that were not possible before. These digital representations can be used for a wide range of applications, from predicting equipment failures in manufacturing to optimizing energy consumption. The use of digital twins is overgrowing and is poised to significantly impact many industries in the years to come. What is a digital twin? How does it work? Imagine you have a toy car and you want to make a perfect copy of it. So you take a bunch of pictures of your toy car from all angles, measure its size, and note down all its special features. Then you use all this information to create an identical replica of your toy car on a computer. This computer version is like a twin of your real toy car. It's just digital, existing inside the computer. Similarly, we can create accurate replicas of complex real-world objects like buildings, machines, or even entire cities. And the purpose of these replicas is not just to serve as keepsake memorabilia, but to provide us with useful, practical information that will help us monitor, simulate, manage, and administrate the real-world objects and scenarios with accurate predictive digital models. They help us understand how objects behave under different conditions, helping our planning process. Digital twins, therefore, are computer-generated replicas, or clones if you may, of physical assets, products, or entities that are able to simulate, analyze, and improve the performance of their real-world counterparts. This concept typically involves the following three elements: a physical entity, the digital version of the said entity, the data link which connects both. Digital twins are made in a way that they can communicate with various sensors on the physical entity, allowing them to accurately portray real-world conditions. Hence, digital twins are not generic and contain characteristics that make each twin unique, just like its physical counterpart. Another important factor to remember is that a digital twin is not a simulation. There is considerable difference between the two concepts. A simulation imitates a specific process or operation using a mathematical model. Therefore, it is only present during one phase of the product life cycle, whereas the digital twin is present throughout the life cycle, modeling the behavior of its real-life object. which can therefore be used for monitoring, prediction, and control purposes. How to get one? Unveiling the creation process of digital twins. IoT devices play a crucial role in digital twins, providing real-time data for the digital twin to emulate the physical counterpart. Creating a digital twin involves leveraging IoT devices to gather real-time data, which the digital twin replicates to emulate its physical counterpart. As IoT devices advance, the quality of data they provide improves, enhancing the optimization of the physical entity. Digital twins, in turn, organize and interpret the complex data generated by IoT devices, establishing a symbiotic relationship. They are developed by integrating data from IoT devices with conceptual models like CAD or computer-aided design, enabling simulations and insights for optimizing the physical entity. Meet your many different twins. Types of digital twins. Digital twins are modular, and it is common to have several types of digital twins exist within one complex system. That is, they can be categorized into specific subtypes that relate to different levels of abstraction and granularity in the digital representation of physical objects or systems. Based on the hierarchy with which they are deployed, we can classify them as follows. Component twins or part twins. The most basic unit and smallest functioning component. They represent the components or parts of an asset, like individual sensors, mechanical parts, electronic components, or any discrete element within a larger asset. In a vehicle, for example, a component twin might represent the engine, a specific sensor, or a critical electronic module. In manufacturing, it could represent a particular valve within a complex machine. Asset twins. Asset twins focus on individual assets or objects within a larger system. Here, the interaction of two or more components is represented in the digital twin. An asset can be a machine, a vehicle, a building, or any discrete physical entity. System twins or unit twins. Assets assembled into a complete, functioning system are known as system twins. These are typically associated with representing entire systems or complex entities, often on a larger scale, such as a building, a city, a transportation network, or an industrial plant. Some examples of this type are the city digital twins, smart grid digital twins, and building digital twins. Process twins. Systems working together to create an entire process. For example, manufacturing process digital twins are used in manufacturing to replicate and optimize production processes. Factories use digital twins to simulate how their assembly lines work and find ways to improve efficiency and reduce errors. Why digital twins? Digital twins offer a real-time look at what is happening with physical assets. Implementing a digital twin strategy can bring several benefits to an organization, including cost-effective R&D. Digital twins can replace expensive physical prototypes while providing more data that will give valuable insights before starting production. Improved efficiency. Organizations can analyze and optimize their operations in real time by creating a digital replica of physical assets and processes, improving efficiency and reducing downtime. Enhanced decision-making. Digital twins can provide real-time data and insights, allowing organizations to make data-driven decisions and respond quickly to environmental changes. Predictive maintenance. Digital twins can monitor physical assets and identify potential problems, enabling organizations to perform maintenance before any breakdown occurs. Increased flexibility. Digital twins allow organizations to simulate different scenarios, evaluate the impact of changes, and make decisions before implementing them in the physical world, increasing flexibility and reducing risk. Improved customer satisfaction. By providing customers with real-time information and insights, digital twins can enhance customer engagement and satisfaction. The challenges and risks of using digital twins. Using digital twins in various industries offers numerous advantages, but it also comes with its fair share of challenges and risks. Some of the most pressing challenges and associated risks are as follows. Challenges: data integration. Gathering and integrating accurate and high-quality data from various sources can be complex and costly. Inaccurate or incomplete data can lead to unreliable digital twin models, undermining the effectiveness of the technology. Data privacy. Storing and managing sensitive data within digital twins can raise privacy and security concerns. Inadequate security measures can expose sensitive information to cyber threats and data breaches. Technical complexity. Creating and maintaining digital twins requires specialized skills and technology. This can be technically complex, requiring expertise in data analytics, modeling, and simulation. This complexity can deter smaller businesses or organizations with limited resources from adopting digital twin technology. Cost. Implementing and maintaining digital twins can be expensive, especially for large-scale or complex systems. High costs may limit the adoption of digital twins, particularly for smaller businesses or public organizations with tight budgets. Interoperability. Ensuring that various systems, devices, and software can work together to support digital twins can be challenging. Lack of interoperability can hinder data sharing and collaboration between different parts of an organization or across industries. Then, there are also the following risks to consider. Security. Digital twins may be vulnerable to hacking, cyber attacks, and data breaches. Reliability. The accuracy and reliability of digital twin models may be impacted by errors or inaccuracies in the data used to build them. Compliance. Ensuring that digital twins comply with relevant regulations and standards can be challenging. Liability. Using digital twins in critical systems and decision-making may raise liability concerns. Summing up, we see that organizations must carefully weigh the pros and cons of digital twins, implementing strong measures to minimize risks and maximize benefits. This includes investing in data governance, security, training, and risk mitigation strategies. Real-world use cases for digital twins in different industries. Let us now take a look at some real-world instances of utilizing digital twins. Automotive. The automotive industry utilizes digital twins to simulate new designs and concepts, providing valuable insights into their performance before they are physically constructed. Volvo has recently stepped up its presence in the digital twin space by introducing this technology in various parts of its business, from prototyping to creating a more immersive buying experience. Manufacturing. This is the area in which the use of digital twins has gone along the furthest. Digital twins can simulate and optimize the entire production process, which includes designing and testing new products, evaluating assembly line efficiency, and predicting maintenance needs. Siemens, the German multinational conglomerate, has adopted digital twins in an approach to cover the entire life cycle of assets, from their design and production to operation, servicing, and maintenance. Utilities and energy. In the energy industry, digital twins can model and optimize power plants, wind farms, and other energy-generating assets to improve efficiency and reduce costs. These systems can also assist in transforming job-critical training, into interactive virtual reality environments. Disaster management. The effects of global climate change have recently been felt all over the world. Digital twins can help to mitigate these effects by allowing for the intelligent design of more innovative infrastructures, emergency response plans, and climate change monitoring. By making digital twins of cities, disaster management efforts can be coordinated more effectively, reducing the loss of life and property. The Shanghai digital twin is an excellent example. Retail and e-commerce. In retail, digital twins can be used to model and optimize store layouts and product displays, helping to improve the customer experience and increase sales. Fashion retailers such as H&M and Zara have adopted digital twins to improve their presence in the online space and gain market share, while e-commerce brands like Amazon and eBay use this technology to help customers better visualize products. Aerospace. Designing and manufacturing products like aircraft and spacecraft are so expensive that it is crucial to complete tasks accurately first to prevent costly delays. Digital twins enhance decision-making by enabling teams to visualize and interact with computer-aided design models and other datasets in real-time 3D, from design and engineering to assembly and maintenance. Healthcare. In healthcare, digital twins can model the human body and simulate medical procedures, such as surgeries and drug treatments, to improve patient outcomes. Systems have also modeled the flow of people through hospitals and tracked where infections may exist and who may be in danger through contact. The digital twin concept is revolutionizing the business world by combining artificial intelligence, the Internet of Things, and data analytics, resulting in limitless potential and significantly enhanced business value. Digital twins have sparked a revolution in product development and operations management, harnessing the power of virtual simulations for unparalleled insights and efficiency. With their boundless potential and growing prevalence, digital twins promise to ignite a new era of innovation, offering thrilling solutions to the most pressing challenges of modern industries. Get ready to witness the accelerating transformation of business as we know it. Signing off, Katina Media, the premier source for your tech news and information.